Hi everyone. So next week we're going to start chapter 4 differentiation, which is the last chapter of your final exam. I would like to use this video to help you to prepare for this chapter before you come back to school. Okay, so let's start by reviewing the concept of slope. Okay, so we all know slope can be given by y2 minus y1 over x2 minus x1. Okay, well, x1, y1, and x2, y2 are 2 points on the straight line. Okay, so I think all of you get the idea, and I don't need to further explain it. What I want to stress is y2 minus y1 here refers to the change in y, and x2 minus x1 here refers to the change in x. Okay, so actually slope gives us a quantity that describes how will the y change for every one unit change of x on that straight line. Okay, therefore, for example, if the slope is positive 2, then that means for every 1 unit increase of x, y will increase as well by 2 units. Okay, that's the basic idea of slope. Okay, in order to make the whole expression become easier, sometimes we may use delta y over delta x to describe the slope. Okay, delta y refers to the change in y, delta x refers to the change in x. Okay, I think you have learned this notation in physics, so I don't want to further explain it. Alright, so now the question is, what if we expand the idea of slope not only to straight line but also to curve? Okay, so let's see. If I give you a curve, y-axis and x-axis, curve. Okay, so this looks like an exponential curve. Okay, you can try to imagine it is 2 power to x. Okay, but actually it can be anything. Maybe a sine curve, maybe a cosine curve, whatever. Okay, so if we give you y equal to fx and ask you to calculate the slope, okay, then what you did on straight line cannot be applied here, because if you randomly pick 2 points on the curve, they will give you to calculate the slope, then it is meaningless. Okay, try to imagine this. We can pick out any 2 points on the straight line to calculate the slope, because the slope of a straight line is always a constant. Okay, it will not change its steepness. But for a curve, the slope for any 2 points of a curve is always changing. Okay, so you can see this part is flatter, this part is increasing and become steeper and steeper. The increasing rate becomes faster and faster. Alright, so you can see there is no way that we can pick out any 2 points of a curve to calculate the slope. But what if we still want to study the behavior of the slope, of the curve y equal to fx? What if we still want to know how will it change along the x-axis, whether it will increase or decrease? Okay, so then we have to figure out how to find out the slope of a curve, not the same way as straight line. Okay, so we figure out not to calculate the slope among 2 points of a curve, but only 1 point. Here. Okay, so this is how the whole things go. For example, now y equal to fx, I pick upon A, and the y value obviously can be given by fa. Okay, so I think no one will disagree this, right? Okay, so and also I imagine that there is a point B. Which is very close to A. And by close, I mean they are nearly the same points. Okay, so how to make B and A become the same point? We can say if b and a, okay, for example, if b equals to a plus h, and if I want b and a to become the same point, there's only one way, okay, is to make distance between them become 0. That means I want h tends to 0 to become 0. So now we can imagine this. If b equals a plus h and h tends to 0, then that means b tends to become a. Okay? Then b equals to a plus h tends to becomes a. Alright? That means actually a and b are in the same position on the x-axis. Okay? Nearly the same position, I should say. Okay? The limit of b goes to a. Alright, so then we can see the y coordinate of this point B will be given by FB, okay? But it also will be given by FA plus H. Okay, now if we want to calculate the slope between these 2 points, we can say that now the slope can be given by FA plus H minus FA divided by a plus h minus a plus h minus a. And if you are paying attention enough, then hopefully you can see the denominator part a plus h minus a will become h only, okay? And no change to the numerator, fa plus h minus fa, which is the same as the previous equation. Okay, so now we can define slope in this way. Imagine a point B that is very close to A, okay? And how to make them become very close is to make h tends to 0, then they become very close. Alright, so and then fa plus h is the y value given by point B. Fa is the y value given by point A. So then we can simply use this method to calculate the slope of these 2 points, okay? But these 2 points are actually the same point. I use orange to indicate that these 2 points are actually the same point. So to calculate the slope between these 2 points is actually we're calculating a very small part of this straight line, of this curve, sorry. Okay, we're calculating a very small part, the slope of a very small part of this straight line. Okay, you can try to imagine that every curve is formed by infinitely many little straight line fragments. Okay, for example, you can imagine this. A very daily life example is, okay, this is the Earth. Okay, we stand on the Earth. Okay, and the Earth should be a sphere shaped. Okay, we stand on the Earth, but we cannot feel. Okay, we don't think Earth is a flat. It is round. Sorry, is a sphere, because when we look at the ground, it's flat. Why this happen? Because we are too small comparing with the Earth. Okay, so the curved surface of the Earth, to us, it looks like a flat ground. All right, so maybe too far away from the contents here. Okay, so you can imagine that if I give you a curve, actually it is formed by infinitely many straight line fragments. Okay, so all these little points join up. If I add infinitely many points to a curve, okay, then for any 2 adjacent points, the curve looks like a straight line. Do you agree with me? Okay, so I think so. Okay, so the idea of calculating the slope of a curve goes like this. We try to imagine, okay, if we break down the curve into so many small pieces, okay, then for any 2 points that is very close on the curve, it will look like a straight line. Then we can do the same thing as what we do as in the straight line equation, okay, to calculate the slope by simply y2 minus y1 over x2 minus x1. Okay, the key is to try to calculate the slope among two very close points on the curve. Okay, so you can do the same thing to any points of the curve. All right. Okay, so this is the slope. Go back to here. This is the slope of. Sorry. Okay, let's correct this. Sorry, give me a sec. It's quite hard to control this. This is my first time to use this. Sorry. Alright. Okay, so this is the slope. This is the slope of y equal to fx at x equals to a. Okay, because point B is the is the point we imagine that is very close to a. So actually, this is the slope of y equal to fx at x equals to a will be given by this formula. Yay. Okay, but when you try to really calculate this, you find there is a problem. Why? Under the assumption h tends to 0, then this cannot be calculated. Okay, but don't be afraid. In chapter 3, we have learned the idea limit. Okay, when h tends to 0, this thing cannot be calculated, but in the world of limit, it can. All right, so now we can say actually the slope here should be given by limit h tends to 0, fa plus h minus fa over h. Okay, in order to make the whole thing become general, okay, so let's make a general definition for this idea. Okay, so the slope of any given point of y equals to fx, any given point, okay, can be given by, okay, the slope here can be given by limit, okay, fx plus something, okay, plus some change, okay, x refers to the a here, okay, and I want this little thing called delta x, okay, the change in x, and don't forget the change in x needs to be very small. Delta x needs to be very small, okay, delta x is a number, it indicates a change in x, okay, minus fx over delta x, okay, these two formula are exactly the same. X is replaced by a, h is replaced by delta x, okay, a is replaced by x here, okay, so the slope here equals to limit delta x tends to 0, fx plus delta x minus fx divided by delta x, which is exactly the same, and we call this idea the first principle. Okay, to calculate the slope of a curve. Okay, all right, so now give you some new notation. Instead of calling this a slope, we want to give some fancier name. Okay, we need to because this is calculating the slope as well, but this slope is kind of different from what we do in the straight line, so we want to make them sounds like different, so let's just call it dy over dx. Okay, why not simply use delta y over delta x back, because first I use delta x here to refer to the change here from a to b. Okay, so I should not use delta x because it will duplicate the symbol that I used. Okay, so then I use d to indicate difference this time. Okay, dy indicates a very small change in y, dx refers to a very small change in x. Why the change need to be very small? Because this is a curve. All right, easy to understand. Okay, so maybe the whole idea freaks you out. Okay, let me give you some concrete example of how we do this. Okay, for example, find dy dx if x equals if y equals to x squared by first principle. Okay, so how to do this? Simple. By using the definition, dy dx equals to limit delta x tends to 0, fx plus delta x minus fx, and then over, sorry, don't know why it got some delay. Okay, over delta x. Okay, so fx plus delta x here. Now we can say if y equal to x squared, that means fx equals to x squared. The function now is x squared. So fx plus delta x, we replace this x by x plus delta x. So it equals to x plus delta x squared minus x squared. Okay, don't forget the limit. Limit delta x tends to 0. And then over delta x. Okay, so this is not a very difficult question in limit. Okay, easy to calculate, far more easier than what we do in chapter 3. So x plus delta x squared can be expanded. Okay, even the Form 2 students can expand it. X squared plus 2x delta x plus delta x squared minus another x squared. So this 2x squared can be cancelled later, but we leave it for the next step. Over delta x. Okay, sorry again for my poor handwriting. Over delta x. Okay, and then we can see this x squared is cancelled with this negative x squared. Okay, and then the whole thing becomes 2x delta x plus delta x squared. Limit delta x tends to 0. 2x delta x plus delta x squared over delta x. And it's very obvious that we can simplify delta x as well. Then the whole expression will become limit delta x tends to 0, 2x plus delta x. Okay, here, because this delta x is cancelled with the denominator, this delta x squared, one of the delta x is also cancelled with the denominator, so the whole expression, only 2x plus delta x left. Okay, so now, does this limit exist? Okay, far back from the first step, we don't think this is exist. We can't figure it out. Okay, but after doing some easy simplification, we can see delta x tends to 0, then this limit tends to 2x. Okay, so that means geometrically, if I give you the function fx equal to x squared, a parabola, then the tangent of any given point, then the slope of any given point of this curve should be given by 2x. That means at x equals to 1, the slope will be 2 times 1. That is, put x equals to 1, then the slope will be 2. Okay, at x equals to 1. Okay, but we'll explain it later on. Okay, so I want you to try to practice this whole idea of first principle finding out dy over dx by using first principle. Okay, and what will this what can we use this to calculate? Okay, we'll cover it later. Okay, so this is how we solve the questions. Okay, so I want you to try one question at home, which is very similar to this. Okay, answer me during the lesson. Okay, so homework, I want you to try to figure out dy over dx if y equals to x power to 3 this time, x power to 3, not x power to 2, not x squared, but x power to 3 this time. Okay, find dy over dx if y equals to x power to 3 by using first principle. Okay, so this is a simple question for you to practice at home. Okay, hope you enjoyed the video. Okay, maybe not. See you next time. Bye.